Alright, so I want to go through a couple examples of thermal equilibrium problems. Thermal equilibrium problems are prime examples of conservation of energy, where the energy or heat lost has to be equal to the heat gained by another particular object. So as an example, this particular question talks about a piece of iron being dropped into a glass of water, where the iron's really hot and the water is fairly cool. Okay, so if we think about this in terms of heat, the iron is going to lose some heat. It's going to cool off in the water. However much heat it loses, it must give to the water. Okay. Now, we have expressions for the amount of heat. Now, and if we sit and we read the problem itself, a piece of iron of mass 200 grams and a temperature of 300 degrees Celsius is dropped into a 1 kilogram of water at temperature 20 degrees Celsius. What will be the eventual temperature of the water? So this is when they reach thermal equilibrium. Technically, both the iron and the water will reach the same temperature. Okay, and it says take the specific heat for iron to be 470 joules per kilogram degrees Celsius, and for water to be 4,200 joules per kilogram degrees Celsius. Okay, so there we have an expression for Q if we're given specific heat. It's mc delta T for the iron, and we'd have mc delta T for the water. Now, one particular helpful tidbit for solving these problems is to think of delta T as always positive. Okay. Now, this might end up being a little tricky, and if it is, we can talk about a different way to do this, but I think ultimately it makes some sense. For this particular object, when the heat is lost, okay, the mass of the iron was 0.2. Its specific heat is 470, and its change in temperature, well, it's going to lose temperature. But if I want delta T to be a positive quantity, okay, then it's going to start at 300 and it's going to reduce down to some temperature. Okay. On the other side, water is going to heat up. So the mass of the water was 1 kilogram. It has a specific heat of 4,200. And its change in temperature is really going to be a temperature minus its original temperature, because it's going to heat up. Now, there are alternative approaches to this, but in these problems, it's best to keep the delta T's as being positive quantities. Okay, so now that we've got this whole thing set up, this really just becomes an algebra problem, like where we have x, and we need to solve for x. So over here, on this side, we've got 4,200t, and then 4,200 times 20 gives us this value. Over here, do the 0.2 times 470 first, and then multiply that by 300, and you get 28,200. And if I do that, same thing times t, it's 94t. And now I can bring this over to the other side. So add 84,000 on both sides. Okay. And I'll subtract 94t from both sides. Oh, I'm sorry, this is negative, so I'm adding 94t to both sides. So I get this value. And now divide. And we get that our final temperature of the water and the iron cube will be 26 degrees Celsius. Okay, so that's kind of the thought process behind this type of problem. Now, I'm just going to set up the other one for you, and then I'll have you guys go ahead and try to solve it. But it says an ice cube of mass 25 of mass 25 grams and a temperature of negative 10 degrees Celsius is dropped into a glass of water of mass 300 grams and a temperature of 20 degrees Celsius. What is the eventual temperature? And then it gives us the specific heat of the ice and then the latent heat of fusion of the ice. So this one, again, we're going to start it off by saying, all right, the heat lost by one thing will be equal to the heat gained, oops, spelling would be good, by the other. Now, if you put ice into water, what loses heat is the water, and what gains heat is the ice. But this is going to be a little trickier, okay? Now, the heat lost by the water is not going to change into a different form, okay? So you just got mc delta T. But ice is going to go through a change, okay? First and foremost, the ice is going to have to heat up to 0. So it's going to have to undergo a specific heat change for the ice. Okay, this is why they give us the specific heat capacity for the ice, because we're actually going to have to warm the ice up before it melts. It's at negative 10. It's got to get to 0 before it melts. So this is to heat ice to 0 degrees. Now, once we have the ice up to 0 degrees, now we have to have it undergo a phase change, which means we're going to have to take that mass of ice and change its phase. Therefore, we need the latent heat. So this is to melt the ice. Okay. And then once we've melted the ice, we're going to have to heat up that water with the heat that is lost by the other water. So we're going to have to do another mc delta T, where this is to increase the former ice to some temperature. Okay, and the heat that is lost by the water when we put the ice cubes in there is going to do all of this. Okay, so this is not too terrible. Okay, the mass of the water was 0.3. Okay, the specific heat from the water I'm going to take from the previous problem, which was 4,200. Okay, and its change in temperature is going to be 20 minus some value. It's going to get smaller. Okay. To heat the ice was 25 grams, so that's 0.025. And the specific heat capacity of ice was 2,200. And we've got to heat the ice up to 0. So if it was at negative 10 and we're heating it up to 0, then its change in temperature is 10. And then once we have that ice up to that particular temperature, we're going to have to heat it. So the latent heat is 334 kilojoules. So this is in joules and that one's in joules. So we've got to put this one in joules as well. So that'd be 334,000 joules per kilogram. And then we're also going to have to increase its temperature once it's actually liquid, which means it's going to be water. So I'm using the specific heat of water, and its change in temperature will be from 0 to whatever temperature it's at, so I can just leave that as T. And now, again, it just becomes an algebra problem.